So welcome once again. This is the lecture number 22 of the machine learning course. In this session, we are going to talk about the graphical models. And one such model is a Bayesian belief network. So we are going to see the details of this particular model. Uh, Before going to the class, let me tell you that what are the things that are going to come. So this is going to be with respect to the what we were doing earlier. So you know that we were talking about something related to the Bayesian learning. So then in the Bayesian learning, there are a few issues such that finding out the right probabilities because number of variable could be very large, could be very difficult. So there are some assumptions that the people make, and however they simplify the things, but still it doesn't look like that we are going to find out the exact thing. So if you want to do the exact thing, you have to model the word in some ways, and if you can model the word, then you can find out the interaction between the variable, and then you can maybe easily you can find out that what is going to happen. So with this understanding, we are going to see today that there is a method. Bayesian belief network is going to give you a method that actually enables you to represent the real world dependence of the variables. So how they are, we are going to see in this particular lecture. So that how you can represent things and how you can utilize to find out the probabilities. So a few things would be more clear when the slides would come to you. And today we will be seeing an example, and the example is going to be in terms of the story. And then using that story, we would build upon that. How can we model that the word that is we are talking about into that particular story, and then we can solve the probability problem that we actually do. So some mathematics would come here. So be ready for that. That's not a very difficult thing. Most of the time you may have done this earlier also. So let us talk about the Bayesian learning. You know that what is the Bayesian learning? Here you actually focus that what is the probability. What is the probability of classification, not the probability of the hypothesis. Earlier you were thinking that given lot of hypothesis, which hypothesis is the best hypothesis, but into the Bayesian learning, what we do that we focus that what is the right classification probability of that particular item. And using that, we can tell that what is the classification of a particular item. And we go here because we want to search for the possibility that can we do better than the map. So you know that map is going to be a very wonderful thing because map not only take care of that what is the current value, but map also considers that what is the prior knowledge that we have. So on some hypothesis, if we have the higher probability of that particular hypothesis, we multiply this value that with the classification of that particular item, and we give more what is this particular item. So coming out of that, we have seen in the last class that there is some notion of the Bayes optimal classifier. So we have seen that there was a classifier, Bayes optimal classifier, and Bayes optimal classifier give you the classification. For example, if it gives you the classification Vj, 1 minute. It gives you the classification, if it gives you the classification Vj, that is coming from the set, for example, V. What is the V? You know that the classification V could be the set from where the values are there. For example, positive, not negative are two classes. Vj could be the positive or negative that actually maximizes this particular quantity. What is this quantity? For all the hypotheses which are there in your space, you want to find out that what is the probability of hypothesis given the data. It's not, please note that into the map it was not the given the data, it was actually you have to know that what is the probability, but here it is seeing that what are the evidences available. So what is the probability of hypothesis by seeing the data, and then what is the probability that this particular hypothesis is going to give you the label hj, vj, and then utilizing this particular summation, it gives you that what is the right classification. We have seen that this is the best method, very wonderful method, but the only problem with this particular method was this, that if your hypothesis space is generally is very large, and when the space is very large, you cannot apply this particular summation thing, because most of the time we think that infinite amount of space is there, so actually you cannot apply this algorithm. This is the biggest problem. Then one solution came into the last class that we have discussed, that Gibbs algorithm, that tells that you, since you know that a lot of hypotheses are there and they have the different kind of probabilities, so you pick a particular hypothesis with the probability, that is probability of hi given day. You pick a probability randomly, and when a new item is coming, you are going to apply this particular hypothesis on this particular this data item, and you are going to see that what is the classification. This is not a good method, as you say that there is a probability problem, but you know that most of the time, since you are going to select the items, because you know that if some hypotheses have the high probability, then most of the time it is going to be selected. In terms, it is going to be selected, and therefore most of the time you are going to give me the right classification. So expected must classification result is actually bounded here, and so it is bad, but not that bad. It is means the error, if there the error is e, this particular method is going to error around 2e expected value. Still, there is a problem. You know that your objective is to find out the probability of some probability of vj. For example, there is some label that you wanted to find out, given some attribute a1 a2 dot 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 an. If this is some item is there, you are given this particular attribute. You know that Bayes rule says that what is the probability of a1 dot 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 a and given vj, and probability of vj divided by probability of a1 dot 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 an. So this is the Bayes rule, standard Bayes rule. Here you know that this particular quantity is not dependent upon the VJ because you want to find out the classification. So if you want to do the optimization, you can drop this particular term, and you can say safely, you can say that what is the probability of the upper term, and you say that whatever value of VJ actually maximizes this particular quantity, I'm going to give you an answer. This is the standard method. So we have seen in the last class that there is an issue that finding out, because these variables are very much, there lot of variables are there. So we have to find out all the possible interaction of these variables to find out that what the probability of 4. For example, if I say that a1 is equal to 2, a2 is equal to 1, this value is I specify, then you have to tell me that what is this value, what is the probability. And this finding out this probability, because ultimately I'm asking you that what is the probability. You have to do some kind of experiment and come up with these values. Then only I can give you the classification. I am going to give you the classification, but from you I'm asking that what is this probability. You see that very difficult because it's a lot of variables are there and they are dependent into a very complex way. So we don't know that what is this particular value for the, particularly when this particular set of attribute is very large. So there is an assumption that naive Bayes classifier says, it actually puts the assumption that let's assume that if you specify this particular VJ, then all these things are independent. Quickly, it actually this probability changes, and you say that what is the probability of a1 given vj multiplied by probability of a2 given vj, and you know that here instead of having more variables and finding out their interaction, here I only need to find out that what is that particular value. Let me tell you once again that let's assume that there are n variable. You know that there are 2 to the power n possibilities in which they can interact. Here I'm assuming that all these AIs are going to have the values from 0, 1 only. Let's assume that. You know that these variables, these are the attributes and they can take any value. But for the sake of simplicity, let's assume that they can take only 0 and 1 value. How many values are there? And let's assume that n such attributes are there. So 2 to the power n different values are possible because I can a1, a2, an, I can assign 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0. So you can see that all these values are possible that you can assign. And for each of these cases, you have to tell me that what is the probability. So this finding out this particular quantity, finding out this probability is going to be very difficult. But if I say that, if I put this particular assumption that naive Bayes classifier puts that when you specify this target variable, these things are independent, then this particular value I can represent by just a multiplication of individual term. And you can see that how many attributes are there, n attributes there. So instead of 2 to the power n, you actually reach to the place where only n values need to be specified. And this is the reason that this becomes tractable. Otherwise, it was not being tractable earlier. So that's why this is a highly practical method. We have seen in the earlier cases that this is the thing. But now I want to tell you a very important thing, that is it a right thing to have this kind of assumption? How many of you would be agreeing that is it a right assumption to have this kind of, is it a right thing to have this kind of assumption? Do you agree with this? As it looks weird that we don't know about the problem and we are having this kind of assumption. How can we have this kind of assumption? So that's why we are into the problem. And to solve this kind of problem, what I suggested a few minutes back, that you have to represent the word, means how these variables are interacting in some way. And that is how we can represent, we are going to see. So if we can represent this thing, then we can find out this particular value in more effective way. So this is the one way for the naive Bayes classifier. But if we can represent we represent the interactions in the right way, then we can effectively find out, means more suitable value we can find out of this particular quantity, and that would be more logical thing to do. Make sense? So in the hunt of finding out this particular value, we are going to see that what is the right way to find out to this particular value, instead of just saying that all these things are conditionally independent. Okay, so this is what we wanted to do today. And before going to that, let me give you bring you something from the probability that you already know, that if I want to find out probability of A and B, it is going to be the probability of A multiplied by probability of B given X. What does it mean? That let's assume that X and Y, A and B are two things, and I want to find out what is the probability of A and B. This is what the probability I wanted to find out. So you can say in this way that let A happen. So what is the probability of A? Then inside the A, this particular thing happen. What is this? This is the probability of B given A, because A had happened, and inside this. So you can write this expression into this particular way, that you can say that probability of A and B is equal to probability of A into probability of B given A. And you know that in this setting, why you are going from this particular side, you can go from this particular side also, you can go from second side also. Here, if you from this side, if you go, you can say that it is the same thing, that if you say that what is the probability of B multiplied by probability of A given B. Okay, so ultimately when these two things are same, you can equate them. You can say that probability of B into probability of A given B, this quantity is equal to this original quantity. I can say that they are equal. So if they are equal, then what can I do? Okay, so if they are equal, so I can take an advantage. I can say that what is the probability of A given B is equal to probability of A into probability of B given A divided of probability of B. And this is a very celebrated result. What it is called? It is the Bayes rule. It is a Bayes rule. So we can see that this is a very interesting formula, and many other time we are going to use it. So please be comfortable with this. That what is this? Probability of A and B is equal to probability of A into probability of B given A. Here XY is written. I am telling AB. So there is something called independence. If two things are independent, means what? That probability of Y given X is equal to probability of Y. Why? Because whatever value you set over here, it is not going to have any effect on the probability of Y. So if there is an independence, you say that probability of Y given X is equal to probability of Y. And if you put this thing over here, that so therefore into the cases when there is independent, we say that probability of A and probability of B is equal to, you know, that probability of A multiplied by probability of B. And you see that here, if you put probability of Y, same equation you are going to get over here. Bayes rule we have just discussed. There is a very interesting concept that is called the marginalization, and this is a very interesting idea that actually says that if you want to find out if you know that what is the interaction between X and Y, there, let's assume that in your system there are two variables, and you know that what is their probability. Let me tell this thing, for example, X and Y. Okay, and let me say that X is going to have 0 0 0 1 1 0 1 1. Let's assume these values are there. What is the probability of XY? Means what is the probability that X is equal to 0 and Y is equal to 0? Let's assume that the probability is 0.1. What is the probability that X is equal to 0 and Y is equal to 1? Let's assume that the probability is 0.2. What is the probability of this quantity? I don't know. Let's call probability 0.4. What is 1 0? Okay, what is the probability that X is equal to 1, Y is equal to 0? So this is the joint probability, that is finding out how to find out this joint probability. I'm not talking about. Let's assume that somebody has given me this value. So what is the probability of that? This is going to be 1 and 1. So since the summations need to be 1, it is 4 plus 5, 6, 7. It is going to be 0.3. Okay. So this is the actually, let's assume that this is the table is. Once again, let's assume that this is the table where you know that what is the joint probability. Somebody had told you that what are the joint probability. If you know the joint probability and you want to find out that what is the probability of X for one variable only. If you want to find out what is the probability of X. So how can you find out this? So if you want to find out the probability of X, and definitely it would be specified, for example, what is the probability of X equal to 1. So it is going to be that you find out for all the values of summation of Y. Summation of Y means for all the values of Y, you find out the this particular thing. What does it mean? It means that if you want to find out the probability of x, it is going to be the probability of x is equal to 1 and y is equal to 0 and y is equal to 1, because here in our particular example, the y can only take two values. So x is equal to 1, probability of this is the summation of these two quantities. This particular equation says this. Okay, if you want to find out this, you can find out the summation. So help me to find out what is the probability of 1, 0. 1, 0 is equal to 0.4 and the 1, 1 is equal to 0. Plus 0.3. So it is 4, 5, 6, 7, 0.7. The probability comes out to be 0.7. So we knew what we were aware of. We were aware of the joint probabilities. We were aware of the joint probabilities. And by this we were actually we were aware of the joint probabilities, and by this, if we wanted to find out the probability of a particular item, one item, so we can marginalize one thing, we can remove one variable. Okay, this is called the marginalization. So here, into general term, we can say that, let's assume that lot of variables are there, 1, 2, 3, 4, I minus 1, then there is xi, then I plus 1 and in. So you can see that in this particular thing, xi is missing. And here, if you see that joint probability of all these things are available, you just find out the summation of x. Summation on all the possible values of x, you find out the summation of this thing, then this is going to give you the probability where xi you can remove, marginalize, you can remove this. This particular thing is called marginalization, and it is going to be a very interesting idea. Okay, sometime you also know that there is something called conditional independence. Few lectures back, we have also talked about this. What is the conditional independence? Let's assume that that there is no independence between x and y, means it is not equal to probability of x into probability of y. Let's assume that it is not like that. It is not like that. It is not like that. But sometime it may be possible that if you introduce a one more variable, you say that xy given z, there is one variable, and if given z, it becomes the multiplication. This multiplication becomes okay. So it says that now there is an independence given this particular condition. We have seen that in the previous class, few classes back, that how graphical representation can help us to understand this particular thing. So if you specify any other variable, and by this independent is assumed, we say that it is conditional independence. Few mathematical things are there. So let us solve a small problem. And here I'm going to call about that there is some table that is called the soft XOR. Okay, so what is this particular table? Let's assume that two variables A and B are given. And you know that what is the output of XOR? 0 output is 1, 1, it is 1, 1, 0, it is 1, otherwise it is 0. This would be the output of the XOR. But here, this particular table actually is going to give you a value that what is the probability that C is equal to 1. What is C? C is the output. Okay, C is the output. So let's assume, I think this is the symbol of XOR. Am I right? Am I right? If you say that A and B over here, you get C value over here. So what is the probability that C is equal to 1 given X, given A and B? If you specify these two values, what is the probability? It is, because you know that the value should be what it should be in this particular case. In this particular case, what it should be? 0, 0 should be 0. So what is the probability of 1? It should be 0, but there is some probability. Let's assume that there is some faulty circuit that is going to give you some time 0, 1, there is some problem. So that's why I'm telling that it is soft XOR, there is some problem. So the 0.01, it should be 0, but it is 0.01. What is the problem? When it is a 0, 1, it should be 1, because this probability should be 1, because it should be 1. But here the probability 0.99 means in 100 cases there is some flaw. So similarly, 1, 0, it is 0.80, lot of flaw. 1, 1, it should be 0, but probability is 0.25. Let's assume that these are the probabilities given to us. Any problem in this particular table? Let's assume that I'm feeding A with the probability 0.65. I'm feeding B is equal to 1 is equal to with the probability 0.77. So in this particular circuit, what I'm going to feed? I'm going to feed A and B, and the probability of feeding A is equal to 1 at 0.65, B is equal to 1 is equal to 0.77. Can you tell me the probability of A is equal to 1 given C is equal to 0? So what happened that somebody have actually find out that C is equal to 0. Okay, what is the C is equal to 0? Then can you tell me that what is the probability that A is equal to 1? Interesting question. Okay, so we have to find out that what is the probability of A is equal to 1 given C is equal to 0. So we want to find out, let me find out instead of this given, if I put the comma over here, what is the probability that A is equal to 1, C is equal to 0? If I want to find out this, again, we can apply the marginalization. We can say that since 3 variables are there and third variable is not there, I can say that means find out the summation with respect to the B and what is the probability of A is equal to 1, B and C is equal to 0. So when I put B means what? For all the values are B. Okay. And you know that you conditional function, we have seen that you can represent that because C is equal to 0, given these two quantities, we can write like this: C is equal to 0 given A is equal to 1 and B. But then these two things, then you have to write probability of A is equal to 1 and B. This thing you have to write probability of A is equal to 1 and B. So you know that these two things are independent because they are input, because you are going to give the input A and B, so they are independent. We assume that they are independent. If they are independent, this quantity is going to be probability of A is equal to 1 and probability of B. So we write into this way. And since it is a summation term, we can expand once we put the B is equal to 0 and then we put B is equal to 1, and we can write this expression as a summation, and then we can find out that what are the quantities. So this particular thing, what is the probability of C is equal to 0 given A is equal to 1 and B is equal to 0? A is equal to 1, B is equal to 0, probability is 0.8. Being 1, so what is the probability of being 0? Is 1 minus 0.8, it is therefore it is 0.2. Everybody understand this? What is the probability of A is equal to 1 given here 0.65? What is the probability of B is equal to 0? So it is 1 minus 0.77, it is 0.23. So the first quantity we have actually evaluated. Similarly, we can find out the second quantity. I leave it on you, it's very easy. Find out that these values are there, then you can find out that what is this particular quantity. Similarly, you find out what is the probability of A is equal to 0 and C is equal to 0. Can you find out this particular probability? You can again apply the similar mechanism over here and you would come up with the value 0.075. I give you a homework that please try to find out this thing, and it is going to be 0.075. We wanted to find out probability of A is equal to 1, C is equal to 0. So you know that this equation, where is the equation? You know that this equation, okay, that you know this equation, probability of X given Y is going to be probability of X and Y divided by Y. So you can utilize this particular thing to find out the quantity. This quantity, it is going to be the probability of, what is this probability? Sorry, this probability A is equal to 1 and C is equal to 0. A is equal to 1 and C is equal to 0 divided by probability of C, and then this quantity comes out to be probability of A given 1, C is equal to 0, A is equal to 1, C is equal to 0. You have computed here. And what is the probability of C is equal to 0? Again, you have to insert the next quantity for the marginalization. Let me say that A has been introduced. A is equal to 1 and A is equal to 0. A is equal to 0 has computed over here. A is equal to 1 is already available. You put these three values over here and you get 0.843. So this is the method by which you can find out you can solve these some of the probabilistic mysteries. Before going forward, the last mathematical thing that I wanted to discuss with you, that this is a very interesting statement, that let's assume that you find out the summation of some variable j for all the values. What is this probability of j given r, and there is some function of r is written over here. Interestingly, this comes out to be the only function of r, because you have find out the summation for all the values of j. It comes out to be this function of r only. So what is the proof? So this is the quantity. So this quantity, you know that probability of j given r is, a few minutes back we have written probability of jr divided by probability of r. We can write into this particular way. And in this particular summation, because the summation is on j and these two terms are actually independent, so I can take it out and I can take this thing as well out. So we are into this particular situation where I'm going to, fr is here and the bottom term is here, and I'm going to find out the summation on this particular thing, this particular quantity. If you find out the summation of this quantity, j actually goes away, because for all the values I have find out, it becomes probability of r, and then it is divided by probability r. It is actually f of r. Very interesting result that after some time we are going to utilize it. Please note down. All right, so a belief network, actually, let us come back to our original topic that we wanted to talk about. So we have, as I have told you, that it is going to be a graphical model. It is going to tell you something about the graphical way, because and that is going to help you to help us to find out various probabilities. Independently specifying all the variable is actually not possible, as we have few minutes back that there were log 2 to the power n minus 1 possibilities were there, because if n attributes are there for any particular variable, if I want to find out that how many other interactions I have to find out. So since they are n minus 1 values, and let's assume that these variables can only take 0 and 1 value. So this particular variable is going to interact in 2 to the power n minus 1 way with the others, with the settings of other variables. So it is going to be very difficult. But by constraining the variable interaction, we can say that these variables cannot interact with each of them. Because what I was thinking, that if I wanted to find out what is the probability that x1 is equal to 2, for example, I want to find out what is the probability that x1 is equal to 2. I have to find out that how summation of for all the values, what is the probability and this particular complete quantity. This was going to be a overkill thing. But if I say that, let's assume that whenever you are going to write this expression, they are only two of variables are only interacting. Let's assume that we know. Okay, our word is this. If our word is such that only two variables are interacting everywhere. So instead of this, we can represent that we don't know that how it is. So let's assume that there is another function that given two variable can tell me that what is the value. Then I can find out the multiplication with respect to the 99 terms, because for every term I see that what is interaction with the others, and just use this thing to find out the things. So that's not easy. Sometime finding out this thing is also not easy, but I'm just going to give you the idea that if instead of all the things, if some kind of things are specified, then you can utilize this. So take it as an abstract model only, that yes, if there is some more knowledge is given, then you can simplify this expression by having some kind of representation. So a belief network actually provides us a framework by which we can represent these kind of things. So when we use these things for the classification, they are Bayes network or Bayesian belief network. Sometimes they are called like that. So let me tell you that what is. Let us go and understand more things about this. So as I told you that we are going to follow a story, and using that story, we are going to actually understand that how we can represent that particular word into the belief network, and how can we find out the right probabilities. Ultimately, our objective, as I told you, is always to find out the probability of this very large term. Let me show you where I have written. I think it was the second slide. So ultimately, our objective would be to find out the probability of this particular quantity. Please note that our task is to find out this particular probability in an effective way. So let me tell you a story, and the story, please focus on this very interesting story. So what was there, that let's assume that there was two houses side by side. There were two houses side by side. One house was of Tracy, and another house was of the Mr. Jack. So in the morning, what happened, that when Teresa was going to the office, she saw that her grass, that she has a grass over here. She saw that it is wet. His grass is wet. So she started thinking that why my grass is wet? Was it a rain last night? Or I forget there was a sprinkler. Okay, there was a sprinkler that actually was there. She thought that looks like that it may be possible that I have forget that I have a sprinkler last night, so it was open till complete night. That's why a lot of water is there. Understand the problem? Two things could be there. She saw that it is wet, so she thought that either his sprinkler was actually on last night or there was a rain. She also noticed that the Jack, who is his neighbor, he also said that his grass is also wet. So what is the probability? Let's say now she want to understand that what the probability that she forget to off the sprinkler at night. Okay, there are two conditions. When she have observed this particular part, this is the second thing. When she had not observed this thing, then what was the probability that she has actually forget to on this switch off the sprinkler last night? And when he saw this thing, this one more condition, then how the things got changed. Okay, everybody understand this story? That let me read for you. One morning, Tracy leaves her house and realized that her grass is wet. She realized that her grass is wet. Is it due to the overnight rain, or did she forget to turn off the sprinkler last night? This is the question she have. She noticed that the grass of her neighbor Jack is also wet. Okay. So this is the condition. Everybody okay with this? I need your yes from your side. Is it clear? Can you write yes that you understood this story, that what was happening over there? Yes? Did you understand that what was happened? Yes? Okay. So let us continue. Let us, because we are the mathematical people, we want to represent this everything into the mathematical form. So let's assume that if I say R, it means that R is equal to 1. If I say that R means rain was there. Last night it was rain. If I say R bar means rain was not there in the last night. If I say that R is equal to 0, it is equal to the saying that R. It is, if I say R, it is equal to the saying that R is equal to 1. So everybody understand what do I mean by R? It was rain last night. What is the meaning of S? The sprinkler was on last night. She forget to switch off the sprinkler. Okay. What is J? Jack's grass is wet. What is J bar? That no, Jack's grass is not wet. Okay, J bar means Jack's grass is wet or Jack's grass is not wet. What is T? Teresa's grass is wet. Okay, what is T bar means Teresa's grass is not wet. So we understand this formula. How many variables we have? R, S, J, and T. These 4 variables we have. Everybody understand these variables? R means anybody. What is R? Rain. What is S? Sprinkler. Was on or not? J, Jack's grass is wet or not? Teresa's grass is wet or not? So in your condition, you know that T is there because Teresa's grass is wet. J's grass is also wet. For S and R, we don't know that whether it was rain or sprinkler was on, we don't know. Okay, everybody understand this thing? So if you want to model the Teresa's word, so how can you model? You can say that because R, S, J, and T, these things are there. Let us model these things. So they have 0, 0, 0, 0. What do I mean by this? Everybody focus on this. Teresa's grass is not wet. Jay's grass is not wet. It was not, sprinkler was not on, and rain was also not there. Okay, looks like very good thing. Looks like that it is a right thing to do. If I say that 1, 0, 1, 0, what does it mean? It means that rain was happened and as sprinkler was not on. Jack's grass is green but Teresa's grass is not green. ऐसा हो सकता है क्या? Can it possible? क्या? एक शेर सुना है आप लोगों ने? कल रात शरारत मेरे साथ हुई कि सारे शहर में बरसात हुई और मेरे घर में नहीं हुई. I'm not sure about that. So the rain was there, but Teresa's thing is not there. However, it is an absurd thing, but it may have the 0 probability. That is fine. Okay, you understand now? What is the probability of this particular event? We are going to represent the probability. What is the probability in your word? You cannot say 1 over here because summation of all these things need to be 1. So there will be some value. Okay, everybody understand 1, 1, 1, 0. What does it mean? That it was not raining. It was not raining, but Teresa's and Jake both grass was wet, and a sprinkler was on for the Teresa. So looks like that it is fine that because she has opened the thing, so her grass is wet. But Jack may also do something. Na? He have his some other mechanisms to water his grass, so it may be given some very less probability, but there will be some probability. That's for the probability. You understand that? Everybody understand this part? Can you write yes? That what is the what are we talking about? Means what is the word? By word, what do I mean by this? Everybody understand this? So how many different values are possible? 2 to the power 4 because 4 things are there. So we need to specify 6. There are 16 states, so we have to specify these 16 probability values. Everybody understand that we need to specify how many probability values? 16. Miloni, you have to specify 16 values. Are you sure? Yes? Okay. However, we know that this particular kind of, because we want to find out the probability of TJRS, it is going to be the probability of T given JRS, probability of JRS. This is the standard formula. Then we can write that probability of JRS into probability of RS. then we can write probability of R is given probability of S. We can represent it this way. So if we represent it to this way, it comes out to be here only 3 variables are there, 2 to the power 3 values you need to specify. Here 2 values are there, 2 to the power 2 values need to specify. One value is there, 2 to the power 1 value need to be specified, because for all the different values of S, you have to specify that what is the probability of R. This only one value. So total how many values you need to specify? 8 plus 4 plus 2 plus 1. How many it is? It is looks like 15. So is it any help? Because earlier you were specifying 16, it is going to be 15. So looks like that it is not any help because it is of the same value. You know that if the probability of head is given, I also need to tell you that what is the probability of tail? It is immediately 1 minus 10. Na? So because of that reason, it is coming to 15. So it is not going to help to me in any way. Now, okay, 15 values you are going to specify. Okay. Now, please focus in this story that there is what is the conditional independence. What are the conditional independence in our setting? We may assume that Teresa's grass's weight depends only directly on whether or not it has been raining and whether or not her sprinkler was on. So we can assume, in this word, we can assume that if we just focus on the Teresa's grass कैसे wet हो सकता है? Only if there is a rain or sprinkler was on. So if I want to find out that what is the probability of JRS, just try to understand what is the probability of JRS, what is the probability of these 3 variables. So here you know that probability of J is not going to affect the probability of R and S. If you want to find out Teresa's grass is wet or not, it only depends on the rain and sprinkler. It does not depend upon the J. This thing, tree does not depend upon, because Teresa's grass is only dependent if there is rain or if there is a sprinkler. If J is watering his grass, how come the Teresa's things would get wet? So there is no direct relation. Let's assume that we know this. Okay. Everybody, are you with me? That what I told you? Yes, I need yes, at least few yes, then only I would forward. Very interesting line. That if you want to find out the Teresa's, whether Teresa's is wet or not, so it is dependent upon rain and only sprinkler. It does not depend upon the J. Yes? Atharva? Gauransh? Rachit? Are you okay with this statement? Yes? Sanidhya, can you write? Miloni, can you write yes? Do you understand this particular formula? Yes, very good. Interesting. So I'm very happy that you understand that these 3 things are, this is my model. Please understand. I'm telling you that in our model, this quantity is equal to this quantity because J is actually unnecessary variable. The things does not depend. So if it is somebody asks me this, you can write this particular thing. It is an interesting observation that we are going to utilize. Next we can find out Jack's grass is wet is influenced only directly by whether or not it was raining. So let's assume that Jake is a person that he is not watering much. So his grass is only depending upon the whether this was rain or not. So we can say that J, what is the J given RS? If I want to find out, it is J given rain only, because it is only depend upon the rain. If S means what? If Teresa has switch on his sprinkler in his garden, in her garden, it is not going to water the J's thing. So that's why probability of JRS is equal to probability of JR. Okay. Furthermore, let us assume that rain is not directly influenced by this sprinkler. If I want to find out what the probability of rain, so if you switch on a sprinkler or not, it doesn't mean anything. Probability of rain is probability of rain. So if they are independent, we can say that these are the conditional independence that we have into our system. So this was the equation that few minutes back we have written. Everybody understand this thing. If we can represent, if we can include our conditional, our word knowledge, then we can say that this quantity is this RS from here. This quantity is actually probability of JR, and this quantity is equal to probability of R. So we can write this expression into this particular simplified way. Now again, I want the yes from everybody, that everybody understand this thing. Can you say yes? Help me to understand. Be happy. You can make me happy by typing yes. Everybody understand this thing? Yes? Nobody is typing. Any problem in this? So once again, let me tell you, this expression was the expression that we have few minutes back C, because it is going to be C that T given JRS and probability of JRS, and this thing's probability of J into RS, probability of RS, same way. We can go ahead into this particular way. This formula is clear. Atharv, can you say yes? This part is clear. So this thing is nothing more than this we are discussing here. So instead of JRS, I'm going to put RS. Yes, RS, I'm going to put RS, RSS. So I can write like this. Interesting. So if I write like this, then how many variables are there? 2. So 2 to the power 2 only. Here 2 variables are 2 to the power 1. Here 1 variable is only there. Here 1 variable is only there. So now I need to specify only 4 plus 2 plus 1 plus 1, they mean 8 variables only. Earlier we were asked to specify 16 variable, but how can we write this expression to this expression? Because we know something from our word. This is the word knowledge that we have. This is something that who is dependent on what? This is the word knowledge. Using this thing, we can reduce the number of parameters. And if we want to specify into the more way, we can say into this particular way. Cut. Now everybody, I need your attention. That if I want to find out the J and Jack and Teresa's thing, if there is a rain is directly going to affect these J and T. But if there is a sprinkler is only going to affect Teresa's house. Do you understand this particular formula, this particular diagram? Can anybody write yes? I'm not expecting that you would be understanding yes. Koranj, is it clear? This diagram is clear? That I am saying this, that two things are there, Jack's grass and Teresa's grass. If it is raining, then rain is going to affect these two things. But if it is a sprinkler is only going to affect this Teresa. Make sense? This thing is fine. This graph is fine. Can you write yes? So if you can understand this was the total thing that I wanted to come over here. This particular diagram, actually that incorporates all these things. Actually important for us. And this is the graphical representation of the word. And it is called the belief network. If we have a belief network, and we want to find out the probability of these things, so it is going to be the multiplication of individual probability term with their parents. So let me give you an example. And this is an example where if this is the, once again focus, if this is the belief network that is given to me, and I want to find out what is the probability of x1, how many variables are there? x3, x4, it is going to be the multiplication of probability of x1 given what probability of x2, given what probability of x3, given what probability of x4, given something. What is given? x1 is dependent upon x2 and x3 and x4. So x2, x3, x4. x3 is dependent upon, x2 is dependent upon x3 and x4. x3 and x4. What is on what the x3 is dependent? It is only dependent upon x4. But on what x4 is dependent? Nothing. So the multiplication of these terms. So we can write this thing expression into this particular way. Here, these three things are parent of x1. So I write that parent of x1 for every variable. See the first variable, second variable, third variable, fourth variable. For every variable, there is a multiplication term. And given what? The parents. All right. So for this expression, what is this? You say that probability of A, it is going to be for this thing, probability of A given what? Probability of B given what? Probability of C given what? Multiplication of these three terms. And you know that A and B are not dependent, so they are directly there. C is dependent upon A and B. So this is what the expression is. Let us see our example, that this is our example. In our example, that you know that, please focus that J and T are dependent upon the rain, and S only influences the T. For this thing, what is the probability? Again, you would be writing that probability of J probability of T, probability of what? R, and probability of S. The multiplication of these four terms. R and S going to be the single thing because they don't have any parent, but for the J, you can see that who is the parent? R. For the J, it is going to be R. For the T, it is going to be R and S. R and S. So this is the formula. This is the same formula which was written over here. This was the same formula that was written over here by this particular diagram. So this diagram actually gives you this independence that whenever a function, whenever you want to find out this value, you can immediately write that what is this particular quantity. And if you can write this particular quantity, your task is done. In this particular setting, when we wanted to find out, in this particular setting, when we want to find out the probability, if you can compute this particular value effectively, then ultimately you can find out what is the Rmax of this particular quantity. Need not to have this kind of assumption, weird assumptions. All right. So interesting idea. So that's very interesting idea that I wanted to give to you. So where were you? I think we were here. We will solve all these problems. Okay. So any questions on that? Once again, remember this particular formula, very interesting formula. Okay, very interesting formula. That for all the variables, you see that who are the parents. Given them, you find out this and multiply all these values. Let us see an example. In our setting only, one morning, Teresa realizes that her grass is wet and the grass of her neighbor Jack is also wet. Let us probability B. Probability of rain is 0.2. Probability of sprinkler, let's assume she forgets out of 10 days, 1 day she forgets. Probability of J is equal to 1 given rain is 1. Every time when there is a rain, J's grass is wet. J is equal to 1 when rain is not there, 0.2. Let's assume that he also does some kind of gardening. Probability of T is equal to 1 when rain is there and there is no sprinkler is 1. When rain is there and sprinkler is 1, this is also 1. Probability of 1 when rain is not there, sprinkler is 1 is 0.9. Let's assume that sprinkler sometime becomes bad also. T is equal to 1, R is equal to 0, S is equal to 0 is 0. Then nothing is there, then how can it could be wet? So, and this is the equation that we have seen. By using the following belief network, can you calculate what is the probability of a sprinkler was on last night? Essentially, we want to find out that given that the Teresa's grass is wet, once again, let me find out the probability that the sprinkler was on last night. This thing, for this thing, I want to find out the probability given that the Teresa's grass is wet. And this comes out to be that is equal to 1 given Teresa's grass is 1. So if you compute, the value comes out to be 0.3382. How it is computed, I would tell you into the next slide. Okay, next slide we are going to compute. So right now, what is important to you that if I ask you that a probability that a sprinkler was on last night, given that Teresa's grass is wet and Jay's grass is also wet, if these two things are specified, then you want to find out the probability of S equal to 1 given T is equal to 1 and J is equal to 1. And this probability comes out to be 0.164. Means if you see further evidences, you are thinking that looks like that it is a very high probability that I forget sprinkler. But if you see that Jack's grass is also wet, then the probability that you forget actually reduces. Make sense? Okay. Because in an exam you got less marks. Okay. So what is the probability that you got less marks? It was very bad because you are a brilliant student. But when you saw that your friend also got the less marks, then you are satisfied. You thought that looks like the exam may be tough. Same thing. Okay. When you saw that others grass is also wet, then you have less problem into that. Okay, so this is how we can find out. I'm just computing this value. Second value is a homework that you can compute by yourself. How to find out this value? S is equal to 1, T is equal to 1. You know that S comma T divided by T is equal to 1. Here then you apply J and R, JRS because only two variables are missing. So you can put all those values over here and go to the marginalization. You can write this particular equation and we know this value because why we are writing this? Because if everything is there, we know that there is an expression probability of J given R probability. We know this equation because of this particular kind of setting. We know that what is the probability when all the variables are there. So we can write this particular expression. In this expression, very important term is there. I have taken this JR1 this JR relationship, I have put this initially over here, and I'm assuming that this is the function of J. Let me assume that this is the function of R. Let me assume that this is the function of R, and this is J given R, and there is a summation on J. So we have few minutes back seen something. Okay, let me show you where. So we have seen this thing. No, no, not this. When we are discussing the probability, I am wasting your time. Let me this using this thing that if you are finding out the summation on this J and there is a function of R, so you write the function of R over here, you can eat up this particular J. So this is the same thing we have done over here in this particular formula. So many slides now. So into this particular thing, there was a J term, and I say that J given R, and it is the formulation of the R, then I can write this particular things over here, and I can eat up this J from here. Similar thing I can do from the bottom also, because here also JR term is there. I can eat up this J. I can say that for RS, this particular quantity. And then for all the values of R, I can write this for R is equal to 1, when the R is equal to 1 and R is equal to 0. So you see that what is the probability of T. All these probability I have specified anyway over here. You can find out from there, here, and put into the formula, you will be getting 0.3382. For the second one, I just encourage you to please read this. So all these things are there on your slides, so you please see this. And last topic that I just would take not more than 2-3 minutes to clear you, that sometime there is some uncertainty into the evidences. For example, let's assume that in three values are there, red, green, blue. If I say that 001, it means that the color is green. Sometime if I say that 010, it means that color is blue. But what if I write the probability 0.6, 0.1, 0.3? So this is called the uncertain evident. I'm not sure that the color is green or blue or green. With the 0.6 probability, looks like that the color is red, and 0.1 probability color is blue, 0.3 it is green. So it is called the uncertain evidences, where we say that what the probability of X given some uncertainty, it is going to be, we assume that it is a probability of X given Y. So with this kind of assumption, if I want to find out what the probability of X on this uncertainty, this Y tilde means there is an uncertainty. So it is going to be, we can, because one more variable we can introduce with the marginalization, we can say that here X and Y, and then we can take this Y second side, we can say that X given Y, Y hat, Y given Y hat. So we know that this quantity we have assumed that it is probability of X given Y. So ultimately we get summation of Y, probability of X given Y, probability Y given Y hat. This particular thing, that how much uncertainty we have, probability of each of these uncertainty things over there. Okay, so if we, this kind of things are there, so in our graphical model we put a dotted circle over here on a variable. So here for this particular quantity, I'm not sure. So there would be some probabilities associated over there. So let me give you an example. Let's assume that the probability of fire when there is a fire alarm is 0.9. So what is happening, that there is some fire alarm going on, and if the fire alarm comes, looks like that the probability of fire is 0.9. Why it is not 1? Because sometimes people may be testing fire alarm. Okay, so probability that when there is a fire alarm, there is a fire is 0.9. Monu said, there is someone who said that he is 70% confident that he had heard a fire alarm. What is the probability of fire? Look, he is a person who is telling that I'm 70% sure that fire alarm was there. He's not sure about this. I want to find out what the probability that fire was there when I'm into uncertain scenario. So as I told you that you can utilize A and use this particular formula, that probability of alarm, probability of F when there is an alarm, probability of A dash. So we can extend it because A can take two values, 0 and 1. So I write this same expression with the A is equal to 0 and A is equal to 1. And then I say that probability of A is equal to 1, probability of A is equal to 0. So what is this fire alarm when A is equal to 0? Fire when A is equal to 0, there is no alarm. What is the probability of fire? So 0.1, because 90% when there was fire alarm, otherwise 0.1. So this is the quantity. Probability of A is equal to 0 when, so what is the probability that uncertainty into the value of A? 70%. So what is the probability that A is equal to 0? Because 70% he is sure, so 30% he is not sure, 0.3. Probability of 1, there is a alarm, 0.9. How much he is sure about that he has heard the amount? 70%. So this is 0.7. By this you find out 0.66. Okay. So again, very interesting thing. So this is the one thing. Then he was when uncertain. He was uncertain that what was happening. Sometimes he may be unreliable also. For example, he knows. For example, sometimes it may be possible that Monu knows that there is a 70. There was a fire alarm, but he is not telling you. So those questions are called the unreliable evidences. And here I asked the Raju, who is the third person. In the same example, let's assume that Monu said that 70% confidence. I asked from the Raju, he is somebody else, about the alarm. It is believed that if the alarm sound, he is 80% it is 80% chance that Raju would tell it sound. Somebody else, this is a second person. He is 80%. If you have heard it, 80% he would be able to tell you. If alarm had not sounded, there is 70% chance that he would tell not sound. So there is a problem. So if there is a problem with the person, he had heard correctly, but there is then he is not going to tell you. Then we can put this dotted line over here. If we put dotted line over here, so essentially what actually this particular what I wanted to tell you, that these things and these things are going to be equivalent, in the sense that if what is this particular situation? Let's assume that there is some house. Let's assume that there is some house where there is some burglary happening. When the burglary happening, some alarm is going to sound. When alarm is going to sound, it is going to be, there is some person G and W who are going to listen that. There are two people who are going to listen this. If I say this thing, it looks like that G has some hearing problem. He sometimes correctly hears, or sometimes he is only 70% sure or some percent sure that even if the alarm is there, he is not 100% sure that alarm has came or not. If I put dot dot dot, means he have heard it correctly, but he has actually he is not telling you. So what I wanted to tell you, that this, since we have seen that this situation we can find out the computation, but if this is the situation, what we can do? Answer is this, that you can put a direct line over here and put the uncertainty into the person's understanding, and if you can push it there, then it becomes the same thing. Make sense? So I think that's all for today.